that, you know, the steam engine lurks behind in everything. I mean, the way the laws of thermodynamics have been formulated is really for the use of the steam engine. Well, here you have percolation theory as another example of a non-thermal. That's an example of non-thermal thermodynamics. There's nothing to do with temperature and so forth, but it has all the machinery of thermodynamics in place. Another example that I know is the non-thermal, the jammed granular packings, the thermodynamics of jammed granular packings that Sam Edwards published in 1989, and which has been running now for 30 years. And Don Frenkel managed to demonstrate that the entropy in that case, which is the number of ways you can pack sand in a box, is actually extensive. That was quite a piece of work. And what I'm going to give you now is a third example, namely immiscible two-phase flow in porous medium. All right, so here's the problem. That's the system you're going to have in mind, and this is work by Marcel Moura. So it consists of these two plates, glass plates, you know, parallel glass plates, and well, actually this one here is not glass plates. This is 3D printed. So it's a two-dimensional porous medium with this kind of matrix here. And what you see here, you're sending in here a mixture of two types of liquids, a black liquid and a white liquid. They do not mix. And what you see here, over here, is steady state here. So if you look at this region here, you will see that the averages, macroscopic averages, remain constant, or they fluctuate about well-defined averages. So this is the system. Now here's a big version of the same system. Namely, this is, again, a Helle-Shaw cell. There are these beads inside here that makes up the porous medium. And you send in a mixture of two liquids here, which are immiscible. They flow in here, they mix, 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 mix. And inside here, you have a steady state. And remember now, in physics, people were very, very excited about injection of one liquid into another one, and you get these wonderful fractals, etc. But that's transient. And that's much more difficult, actually, to analyze this kind of steady state. I mean, it's no wonder that people still have problems with non-equilibrium thermodynamics, but equilibrium thermodynamics is fine. It's a much easier problem, but it's been much, much less studied. All right, so this is what it looks like when you are sending in these two liquids. So you have the system filled with the dark liquid here, and you send in at these injection points here, alternatively, one liquid and another liquid. In this case here, it's actually is air, and this is a glycerol water mixture. So you start out like this. Here's after a while, and here it has reached steady state. And this is what you're going to think about. All right, so here is, what I want to do now is to try to scale up the problem, because when people think about porous media, you're very much into what's happening at the pore level. But there is a continuum level where you're looking at scales so large that actually the pores are so tiny you can forget about it. You can treat everything as a continuum. And the first person who did that was Henri Darcy in 1856. He wrote down this kind of equation, or he had an extensive version of it, showing that the flow rate is proportional to the pressure drop, and the proportionality factor here contains the permeability of the porous medium. That is a reflection of the structure of the porous medium. And then you have the porosity. The porosity you put here just to get this to be the average velocity in the pores. It's just something has to do with time scale. And this is the viscosity of the liquid you're sending in. So this wonderful thing is that this K over phi, that's the porous medium, and here's the liquid, that's this thing here, and that is the entire mobility. So pressure drop gives a velocity in that direction. Now, in 1936, Wyckoff and Botzet generalized the Darcy equation to deal with a mixture of two liquids, immiscible liquids. And the idea they had was that, okay, so here are the two liquids, they're going in there at the same time. And let's say you are liquid number 1. What are you going to see? Well, you're going to see the porous matrix, and you're going to see the other liquid, and they're both going to hinder you, which means that effectively the permeability you see is not the original permeability, but it has been scaled down by a factor, and that factor is this here. This is the relative permeability of the wetting liquid. W stands for wetting, and I have to just correct by, this is the saturation. That's what percentage of the porous volume is actually filled with that liquid. Let's just get this to be the average pore velocity. So you have two equations now, one for each of the two liquids, and they are just basically Darcy equation times 2, one for each liquid. And it is basically that one liquid is seeing the other liquid and the matrix as the effective porous medium. All right, and here comes a important assumption they make, namely that this relative permeability only depends on the saturation, what percentage there is of, in this case, the wetting liquid. Here's how we define it. So this is the physics you put into it. Otherwise, this would be, it's just a reformulation of things. So it doesn't really say much, but now you made a physical statement. But these equations here cannot handle imbibition. Imbibition means if you take the porous medium, a piece of sugar, for example, dip it into milk, and you see the milk rises into the porous medium. It cannot handle that, these equations. So you need something in addition. You have to get the capillary forces explicitly in. And well, you go back to this classic experiment, and here's, the water here rises up in the column because there is now a pressure here, a capillary pressure that is, because of the curvature of the surface, is pulling up, and here's the pressure in the water here, and here's the pressure in the air outside, the non-wetting on the outside, and so the pressure here plus the pressure in the capillary pressure is equal to the one on top, and that's what I've written here. And what you then do is you say, okay, so there are two pressures here. Think now of both liquids actually percolating at the same time. Then you have one pressure in the wetting liquid and one pressure in the non-wetting liquid. And the interfaces between them. And that interface has a capillary pressure, so you call that the capillary pressure. And you make it into a function of the saturation. That's a giant leap. And it's not very well defined. People hate it, but people will use it. But this is it. This is relative permeability theory. That is used in every single calculation that has to do with how immiscible fluids flow in porous media in industrial connections. Right. So what do these relative permeabilities look like? Well, here is for a North Sea sandstone. And these are liquids with different wetting angle between them. We have a surface here, you have one liquid here, the other liquid here, and there's an interface. And the wetting angle has to do with this interface here. So you change that angle, and this is what these curves look like. All right, so now you can go out there and be reservoir engineers, because this is the whole story. One important thing I want to use later on is that if you're dealing with steady state flow, part of that definition is that there are no macroscopic saturation gradients. And the flow here, you will not have a flow going on, So this, you'll go, on average, everything is going to go in this direction here. Not at the pore level, but macroscopically. And that means that the macroscopic pressure gradient is going to be constant throughout the system. That's a steady state. And if this is equal to that, well, the capillary pressure is everywhere equal to zero, the capillary pressure gradient. This is going to be important later on. Anyway, so how on earth can one make this into a give a thermodynamic description of this, a non-thermal thermodynamic description? Well, let's start with the statistical mechanics. And here's once again the steady state. Macroscopic parameters have well-defined averages. But of course, this is a driven system. The moment you turn off the pumps, everything stops. And that means that there's viscous dissipation all the time. Entropy is being generated. You're turning flow into heat. So it looks impossible to do an equilibrium statistical mechanics here. But now look at how one deals with equilibrium statistical mechanics. Here's the gas in 2 dimensions. And because this is an equilibrium, and the definition of equilibrium here is that you're not generating entropy. And what does that mean? Well, it means if I take pictures of this gas, a stack of pictures, one after the other, and I shuffle them, and then I ask you, can you put them back in order? You won't be able to do it. You're not changing the statistical distributions. That is equilibrium. So how can I compare this here, which is not an equilibrium? This is a driven system. This is equilibrium. How can I make a mapping from here to here? Well, it is possible to do that. And this is a way to do it. Well, we start with the gas in 2 dimensions. This is what I just showed you. These are now particles that are bouncing around. Here I draw the space-time diagram for them. So each particle here is tracing out a whirl line. So it's kind of this spaghetti here. Now take a core sample and inject 2 liquids and let them flow through like this. Here are cuts through this sample. The gray here is a matrix, and you have a white liquid and a black liquid. And think of this here, this picture here. That's just like this picture here. Think of, this is now I put in a time axis. What if I treat this as a time axis, the flow direction? And to make it even more clear, this is from Journal of Fluid Mechanics. These are the streamlines of liquids in a porous medium. Here you see the porous medium, just this cut here. Otherwise it's invisible. But look at the comparison here. And the key concept now I'm going to use is Shannon entropy associated with the information entropy sitting here. And steady state, no production of Shannon entropy in the slices. You will not be able to say which one came before another one here. There is no production of Shannon entropy in this system. Yes, there is production of molecular entropy because you're turning mechanical motion into heat. But at this coarse-grained level, there is no production of this kind of entropy. So that you can actually use now. You have everything in place to actually construct the statistical mechanics. So here's a porous sample. Here's a time axis, that's a z-axis, that's the flow direction. I have 2 liquids here, and they are then mixed inside here, and I make a cut like this. The fluid configurations in the plane are in equilibrium in the sense that I won't be able to see which comes forwards. And also in this sample here, look, the total flow rate is constant. It's a constant motion along the time axis. This is just like an internal energy in a closed system. All of this gives us an equilibrium statistical mechanics. Now, if you were to do the traditional way of of getting further now, you would think of go into the microscopic equations of motion and try to deliver or construct a what's it called again? Liouville theorem. I tried for a summer and well, I can't do it. Cannot do it. But you don't have to do it because in the 1950s, Jaynes developed a generalized statistical mechanics based on the information theory. He was trying to develop actually a theory for non-equilibrium thermodynamics. That was his end goal. But he really couldn't do that. But he got everything in place otherwise. And that's what I'm using. So here's the force plug again. And I take out the representative elementary area, not volume, area. And I characterize it by the flow rate through it, by the pore area. That means I'm cutting and making this representative elementary area, and a certain percentage of that area is covered by the pores. That's the pore area. And since there are two liquids here, part of that area has been covered by the wetting liquid. So you have wetting liquid area, you have the pore area, and you have the flow rate here. And then you maximize the entropy. Right? You can write down the entropy for this, and you maximize it, and you end up with, this is the flow rate for configuration X. X means here how the liquids are distributed and how the matrix looks. Here is the pore area for the same configuration. Here is the pore area for the same configuration. Here is the wetting area for the same configuration. And there are three new variables appearing, namely theta, which looks like a temperature. So we called it agitation temperature, or agitor for short. It's a non-thermal temperature. We didn't want to use the word temperature because then people get, to think that's its temperature, but it's not. Then you have this mu here, which acts as a chemical potential. And then you have another type pressure that's associated with the total area. You can think of this the following way. If I have a porous plug like this, and I shrink it like this, that is, using pressure on the system to change the volume. That's what you would say in classical thermodynamics. So you have these variables, and then suddenly you get all the machinery in place for doing a statistical mechanics, not statistical mechanics, but a thermodynamics for porous media, which is not thermodynamics, it's pseudo-thermodynamics because the variables here have nothing to do with thermodynamics, but they just look like it. It's the same formalism. And for example, so here's the average velocity of the liquids. Here's the agitor, here's the saturation, and I do a Legendre transform, and what do I find on this side here as a sort of free energy? Well, that is actually the velocity of the non-wetting liquid. I put a little hat on it because this is what I would call a thermodynamic velocity. I'll get back to it later on. That's when I introduce the common velocity. But anyway, so then you have the flow derivative as it defined, but you also have that the saturation is the derivative of the non-wetting velocity with respect to this quantity here. You would never have been able to guess something like that, yes?
That you have this fluid, right, and then you consider sort of local equilibrium on each slice, right? So this is something also we consider in heat transport models, where you have left reservoir and the right reservoir over there. There is a heat flow, but then you slice it up and say that there is a local equilibrium in this.
Yeah, I have a flow direction.
That is correct, right? Yeah. So when you do that, this slicing, so each equilibrium essentially is defined for a local temperature. So I'm trying to understand what is the intensive variable here for each equilibrium slice.
These are the intensive variables: the agitor, the flow derivative, and the flow pressure. That's what we call them because we don't want to use the usual names for them. But they correspond to temperature, chemical potential, and it's sort of a pressure.
And this is which will vary from the bottom to the top.
Yeah. I have a system here. I can slice like this. You know, you can actually construct this. This is not, you know, this way of doing things you could also use for other systems. Fully developed turbulence in a channel is actually another example that we're working on. But anyway, so you get these kind of things. You have Maxwell relations. Here's the entropy, here's the saturation, here's the flow derivative, and here's the agitor. So you get these kind of out of the blue type equations. You can control the fluctuations. And let's now spend another 6 minutes on developing now, you know, actually how this pseudo-thermodynamics works. So let's start with the Gibbs relation. And this is what it looks like. Here's the total flow rate through your sample. Here's the agitor. Here's the entropy, the Shannon entropy. Here's the flow pressure. Here is the area of that, and here is the wetting area. And okay, if I can change the flow, the average flow rate by changing the cluster structure. That's this one. When you change the flow rate, you change how the clusters look. That's a change in entropy. So that's this part. This one here is a change in pore area. That's what I said. If I, for example, change the porosity, that's going to affect this here in my representative elementary area. And I can have a change in saturation. So this is the Gibbs relation. So what's heat? Well, think of implementing the porous medium on a torus. You know, Santa Nucinia, my close collaborator in Trondheim, he is, in his models, he's using this kind of a donut quite often. And the point now is that if I do the Gibbs relation on this system here, it's a closed system, that means that the saturation is constant, so this is 0, and that I don't change the porosity, so this is 0, then the only way I can change the total flow rate is by changing the entropy. And this is heat. This is heat. I change the pressure, and that changes the way the clusters look, and that's heat. So heat increase in flow rate without change of saturation or pore area. Zeroth law of thermodynamics, well, that you know is if I have to, you know, define a temperature, and you know, in classical temperature, definition there of temperature is what you get from a thermometer. That actually is a definition, but it's closely related to the third law of thermodynamics. So here's the porous medium. I have one porosity here, and I have another porosity here, or one wetting property, one set of wetting properties here, another here. And I send in two liquids here, different velocity and so forth. They have different agitor, and then I remove this bar here, and then up here they mix, and they end up with the same agitor. That's what you need. But that's exactly what the pressure does. You start up with different pressure gradient here and here, but up here, you're going to have the same pressure gradient everywhere, otherwise you'll have cross currents. So actually, the pressure gradient acts as an agitometer. It's a difficult word, it's a thermometer, but it's for agitor. So the agitor is actually a function of the pressure gradient. And the constitutive equation, that's flow rate as a function of pressure gradient, plays a role of an equation of state here. Now, the zeroth law says that if I have three bodies, A, B, and C, and if A and B are in equilibrium, I put them together, they don't exchange energy, they have the same temperature. And if A and C also, when put together, do not exchange energy, they have the same temperature, then B and C will also be in equilibrium. So here is my torus again, and I have one property here, one property here, one property here, And what do I see when these things flow? Well, I can never get a flow that goes like this, because that means I would have a pressure gradient that would go like this. I would have a jump somewhere, but I don't, which means that the pressure gradient has to be the same everywhere. So the third law, no, the zeroth law of thermodynamics is in place. Then the first law, cyclic processes. Now that's one of the places where you can really see that this had to do with thermodynamics, steam engines when thermodynamics was produced. But one can make an analog. So here is a flow going in this direction. These are all porous media. Sending in a flow here with a flow rate QR, agitator theta R, and the saturation like this. And if I now follow, some of it goes out here, but some of it goes in here, and then this gets narrower, so it gets heated up. And this is adiabatic. And here it meets another flow, which in this case here, L is slower. So then they go here, and then you get back here, it expands. So you have adiabatic cooling, adiabatic heating, slow mixing, and fast mixing. This is faster than this. Gibbs relation, and I can actually write it down like this. This is the diagram for that process I just gave you. So this is adiabatic cooling, slow mixing, adiabatic heating, fast mixing. I don't change this one, which means that it's a relation between the change here in the heat input into the system, and here is the work done. And what is the work? Well, that's a transfer of saturation from up here to here. So you actually, this is very complicated to analyze, but this is how you would go about it. All right, a second law of thermodynamics, pseudo-thermodynamics here is, I inject here, and you see here, here's a dark liquid coming in, here's a white liquid coming in, and up here you don't see this anymore. So you have here an non-equilibrium situation going into equilibrium, and that means that the entropy is increasing and then reaches a maximum. This is the second law. The entropy is fixed or increases in those systems. All right. So now we're getting to the co-moving velocity. So now actually, this is a talk I wrote the abstract for. Okay, so here were the thermodynamic velocities as defined in this pseudo-thermodynamic formalism. But this is not what you are measuring experimentally. What you measure experimentally is you have your porous medium, you send the two liquids in, and what you do on the other side is have buckets, and you see how much of this liquid or that liquid ends up in the bucket per second, or per hour, actually. So these are very different things. But it turns out that there's a connection between them, between this seepage velocity that you measure directly and this thermodynamic velocity that you measure indirectly. Namely, this velocity here is this velocity minus the non-wetting saturation times a function Vm. And the same thing with this velocity you measure directly is the thermodynamic velocity plus this wetting saturation times this function Vm. And this is the co-moving velocity. And it turns out this sits outside ordinary thermodynamics. You don't find an analog in ordinary thermodynamics. This is something new. It needs its own equation of state. But I'll get to that. Here's another way of seeing the same thing. I have a wetting liquid velocity and I have a non-wetting velocity. These are without the hats, these are the measured ones. And then you have an average velocity. If you measure the average velocity, can you reconstruct the two velocities? And of course, the answer is no, because there's no unique way of splitting. Right, I have one relation, can I split that into two relations? No, I need a second relation. And that second relation, you can get if you introduce the co-moving velocity. Which means here is the wetting velocity, here's the non-wetting velocity measured, and here's the average velocity, here's the co-moving velocity, and this you can go both ways. So you combine constitutive equations for Vp and Vm to transform and get these two. And why would that be interesting? Well, it turns out that this Vp here, you know, we have the nice regime where the relative permeability works quite well, but there are other regimes where you have non-linearities and horrible things. Now I sound like Trump, sorry. And you would measure this one here. How on earth could you reconstruct these? Well, as I said, co-moving velocity is the thing. And this is how it actually ends up looking. So you start out with this is the average velocity. That's the saturation weighted average. You take the derivative with respect to the saturation. Well, if I take the respect VDS, I get VW, that's that one, and I get minus Vn, this is this one. But then I get the derivatives with respect to the velocities, each velocity itself, which is this part here. This here turns out to be the co-moving velocity. It's not trivial. And then if I just plug that back in here, I have now the co-moving velocity, another expression for it. It looks like this. And here's a two-way mapping. Here's the average velocity, and here's the co-moving velocity. You see the difference between the average here and the co-moving is that I have to take the derivative of this one and this one. That's it. And I can now invert this, and I have here the two velocities of each, the velocity of each liquid, given in terms of the average velocity and the co-moving velocity. So constitutive equations for Vp and Vm give constitutive equations for Vw and Vn, which is very nice when you're dealing with nonlinearities. Okay, so let's look at what it looks, let's find it. What does it look like? So let's use the relative permeability data. This is work done with Subhadeep Roy here and Santanusinia. So here's the co-moving velocity. Here is the two relative permeability equations, and what people do is they give you the relative permeability. The literature is full of the measurements of this. So what we need to do is to get these two here into this one here. So what we do is I just pick out this core here, which is just the wetting velocity if the saturation is 1. So this is V0. Then I can write down the average velocity like this. M here is the viscosity ratio, and here's the co-moving velocity. And then you go into the literature, you simply find Vp as a function of saturation. In the literature, using relative permeability data, these are two types of data sets. Here is the co-moving velocity now in the function of saturation, but here it is as a function of the flow derivative, Vp, dVp, ds. Here's another measurement, another set of data. Look, the average, co-moving in terms of S and co-moving in terms of the flow derivative. There's another set. This was not wonderful, but some data are good and some are not. In terms of being nice to look at. See, like this. Here's another set. Here's another set. Here's another set. And the criterion we used to choose data sets were to have no criterion at all, because, you can't start having a preconception of what you want to find. So it looks like Vm is a constant plus another constant times this derivative. And that was actually predicted, that this would be the good variable, natural variable. That comes from the statistical mechanics. actually, because, yeah, I don't want to get into that. But anyway, this is data that were analyzed by Stefan Berg at Shell in Amsterdam in January, actually. So he took different relative permeability data sets from their big stock, and he found this one, he found this one, he found this one, this one, this one, this one, this one, this one, and it all added up to 43, and all of them were this kind of quality. So it really looks like a straight line. Oop, I turned off the screen. And here is dynamic pore network model data. This is work by Sylvain Proy and Santon Lucinia. And you see also the absolutely gorgeous straight lines. And these are the two coefficients. They depend on the pressure gradient, which you would expect because they depend on the agitator. This is exactly what they should do. And the consequence as well, you have that the two velocities for each liquid is the relation I had before, and this is what it looks like. So it's just two coefficients here. Otherwise, you get everything from this average velocity. Here is some work with the people in Australia and the US. Here are the relative permeability data for North Sea sandstone, Bentheimer, and experimental data here. And this is liquids with different, the only thing you change is the wetting angle. And here is the average velocity and the different wetting angles here. Here is the coming velocity, and you change as a function of saturation, and you see you get this bundle. But if you plot it in the right variable, well, it ends up being straight lines. Here's another data set, same thing, straight lines. Here's the experimental curves. You see there's not much overlap here, but it ends up being looking like this. So, I mean, I have little doubt that there is straight lines here. So what can you do with this? Well, solution to these equations, it has solutions. This is one, relative permeability. This is another solution of this equation. So you actually have an equation here that can give you relative permeabilities that are okay and those who are not. Before, they have always been treated as completely independent, measured completely independently, and you do the best fit you can. But now you actually have an equation for the damn thing. All right, and you can then actually go further. Knowing one relative permeabilities, you can find the other one. If you can measure one with very high precision, you get the other one. And this is the kind of data. I'm not going to go into details here. But let me now, since I have a few minutes left, water ethanol mixture. Now I'm going into real thermodynamics, classic thermodynamics. Forget about porous media. So I have water and I have alcohol, I mix the two. And here is the volume of the mixture as a function of percentage of ethanol. You see it goes from 1 liter down to a minimum here, 0.965, and then up again. I start out with the Gibbs free energy. Take the derivative with respect to the pressure, I get the volume, and the volume. Then I can write like this. This is in all textbooks on thermodynamics of mixtures. So I have a V1 here and V2 hat. These are volumes now, and these are the thermodynamic volumes. This is called partial volumes. This is with the number of molecules type 1, number of molecules of type 2, or moles type 1 and type 2. You get this one. But I can also go in, use molecular dynamics, and measure actually the volumes associated with each of them. And I use Voronoi tessellation here. So these are then particles of type 1 and particles of type 2, and I do this area here. This is the area belonging to this particle here, and I can just add up the two, and that gives me 2 volumes. These are now the Voronoi volumes. Is there a relation between the two? Well, and they have exactly the same form. You see this equation here, and this equation here have the same form. like this. And I go into this relative variables. Xn is degree of concentration of one of the liquids. I have this relation. And then I get a co-molar volume. This I call the moving velocity when it had to do velocities. Now it's a co-molar volume. And what do you find when you do the molecular dynamics? Well, this is a master student. He's doing his master thesis right now. And this is his preliminary data. And damn it, it's a straight line. It's a straight line. Which means that the straight line you see for the co-moving velocity has nothing to do with this being porous medium problem. It's in the mathematics. It's in the mathematical structure. But you can see at the same time, it's not part of ordinary thermodynamics because you don't have this kind of directly measured quantities there. So this is actually an extension. Where does this come from? Well, you can do a dimensional analysis here. The two parameters is A plus B times this V derivative. And you see I divide by V0 here and divide by V0 here. I've written it down. You can see what this is. This is actually an Euler homogeneous function of the first order. I take the derivative with V0 and set V0 equal to 1, and I have this form here. And this is a function. It has to be a function of, I have only one choice, and that's a function of this. And this thing here is a function of like this, here. I cannot do it in any other way. And if I take the derivative of this thing here with respect to Vp derivative, and I take a derivative of this with respect to A, I can switch and they have to be equal. This is a Maxwell relation. So I have a Maxwell relation here. I use it, and that gives me a relation between this F and a B. And then the next thing, and here I have to be unclear because I'm not 100% there in any ways. But what I'm going to say now is if you can find solution to this equation here, and if you demand that this equation, the solution are not crazy, go to infinity or something, you have only one choice, namely this being constants. So this is 0 plus 0 is 0, and that gives you this. Thanks.
So, if there are questions, comments, yeah. Tapoti.
That since you are pumping two liquids,
Yeah.
Is it possible that one of the liquids will flow faster and cut off, the path of another one penetrating, because it is a disordered system? So does it form a pond sort of a thing, a lake, where it cannot penetrate any further? Your simulations of the 3D didn't show any of such pockets.
No, but that is certainly true. You would, this is a two-dimensional system, and you don't see that here. Well, actually, if you do the statistics around this, Marcel has done that. You can see that there are preferred paths. It's a very structured system. And what you see, if you now go down with the saturation, at some point, one of the liquids is going to freeze and stop, and then you go through a phase transition. And the interesting thing is if you go towards, have the wetting liquid freezing, I think it's that one, you will see a jump. That's a hysteresis. But if you go the other way, the non-wetting liquid, when that stops, there's no hysteresis. So it seems to me to be something like a second order transition on one side and a first order in the other side. And when I talk to people who are engineers working in this field, the first thing they say, can you do hysteresis? And I tell them, physics is full of hysteresis. The Maxwell construction in the 1870s was actually set up for this. Yes, we can do that. Hysteresis, I think, comes from this kind of phase transitions happening.
The question. So is it possible that one liquid is moving in, and since the other liquid is moving, and presumably they have two different viscosities.
Yeah.
Could one penetrate into the other to form viscous fingers?
Yes, they could, but remember this is steady state. So what you actually see in practice, if you have a cluster, you will have on one side you have viscous fingers coming out, on the other side you will see imbibition. But these things, when you actually look at this in practice, you'll see these clusters and they break up and they merge and so forth. You really can see the difference between them. So viscous fingers.
You wouldn't be able to see them at the macro scale.
No, you wouldn't be able to. And also, if you look at it carefully, I mean, because the system is too intermingled.
Right.
So when you're dealing with steady state, I don't think you can really distinguish between imbibition.
You
and
have
so
not
forth.
taken that
Yeah,
in the
no,
model.
it's not a good concept.
Any more questions, comments? Just one. I mean, in all these cases, I mean, since basically Darcy's law is there, so if I increase the pressure gradient, even for a single fluid, I mean, there should be next order pressure gradient. I mean, del P square, del P cube, I mean, and these are. I mean, don't you see that, or?
Yes, we do. We do. I mean, the
what
Oslo
does it
group
depend
was the
on? Yeah.
first to see this. The Oslo group saw this in 2009. What they measured was essentially flow rate as a function of pressure, or rather pressure gradient, pressure drop across the system as a function of flow rate. And what they found was that the flow rate goes like the pressure gradient squared. And the reason for that is as you increase the pressure drop, or the flow rate, you are mobilizing more and more interfaces, which means that your effective viscosity, effective permeability goes up, and when you integrate that, you get the flow rate, so that is that exponent plus 1, and it turns out to be around 2.
And for the P square, delta P square term,
yeah,
I mean,
well, it turns out that
what is the prefactor? I mean, you had K and mu. I mean, in this Darcy.
Yes.
I mean, what are the prefactor? I mean, just dimensionally, what are the prefactor?
what you find is V is minus, and you set up a mobility as a function of saturation. And then you have dP, and then the exponent to minus 1 times dP. This would be the equivalent of the Darcy. Where this usually, I mean, that usually is K over phi mu, but here it would be something else, because
I mean, if beta is greater,
that part really hasn't been explored much. But it really is very, very interesting, this, because if you now do pressure gradient here and flow rate, and you take log, you find this, and then suddenly switches over, and then switches back again. This is when you have a channel so open that actually allows flow, and you're not mobilizing any interfaces. And then suddenly you go into this critical region where you're mobilizing more and more interfaces. It's just like if you have a granite packing and you're pushing it more and more and more, you have then more and more grains come in contact, and you see this thickening network. You see exactly the same thing here. And this is, it goes back to linear, because now all the interfaces are moving. And this region here, which is actually quite important, because this is when viscous forces and the capillary forces are in competition, and they are very often are in real processes. That is when relative permeability goes bonkers. You can't do it. I mean, cannot handle this. No way. Cannot. Yeah.
okay.
Then would the two lines, that means the initial slope and the terminal slope, pass through 0?
Depends if the system is percolating, it passes through 0. If it is not percolating, that means you have interfaces that block, you have a threshold pressure. Typically Q would then if it passes, it would be, it would be something like this.
So your
And then
last
otherwise
part-
it would end up down here.
So the last
Sorry.
terminal part.
It would be here. This would be a delta PC, threshold pressure.
But your final part of it.
Yeah, the final part of it, it goes back in. That is when
That's a linear system.
it goes back linear, because that's where all the interfaces are just moving along. You know, yeah.
You got, okay, Deputy, yes, okay, brief one. Shankar, your
Darcy's law.
your talk is low.
Could you have solved
Not
for
loaded, you take
the
your-
Navier-Stokes equation and found out the velocity at every point, you know, numerically? Because this is like the pores are so microscopic, and Darcy's law is more at a macro level.
Yeah.
So, do you think that would be better?
The way we have used this now is that we have used statistical mechanics to sort of put meat on this
Yeah.
pseudo-thermodynamics, and we've been working only on that one.
You would have got
But-
still all your
Yeah.
values.
But you see, I have never in this talk here talked about something like what would be a Hamiltonian-like thing. There's an underlying symplectic structure here, by the way, but we haven't been able to find a good model.
But you
That's
could
all.
have still found the velocity at every point
Yeah, yeah,
for
I
a
get-
given pressure and taking
Absolutely,
into account your viscosity, your
yeah.
everything. I
Yeah.
mean, body force, if you could
This
do
is what
that.
I mean, some of the data I showed is on, part of it is done real experiments, but part of it is halfway experiments in that you reconstruct the porous medium completely, and then you put a lattice Boltzmann calculation on top of it. That means you have all the velocities, everything. Yeah, 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 yeah.
Okay, if no more questions on this, then let us thank the speaker for an excellent presentation and this new developments. And the next speaker is Dr. Shankar Ghosh from Tata Institute of Fundamental Research in Mumbai. So, after 50 minutes.
Thank you for inviting me here. And so this talk is going to be in two parts. And the first part is about compaction, and I'm going to look at rapid compaction. This is something that in engineering is known as dynamic compaction. The second part is what you do in the kitchen. You want to put in some grains, you kind of slowly tap things out and let them settle, and that's the kind of quasi-static compaction that I'm going to talk about. So if I forget, this part of the work was done by Akash Ghosh and Mahesh Bandhi, who is in OIST. This part of the work was done with Akash, Davlevin, Paul Chaikin, and Jay Kumar. So dynamic compaction is something that is typically seen if you want to consolidate your base. You take up a and then you drop the load, that sets up a compaction. And typically what you do is you kind of make a grid, because you see if it goes down, the compaction is like this. So you probably the next time you will compact somewhere here, 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 and so on and so forth. That's one kind of compaction that you come, and this is practically used. I mean, we have all seen in some point of time when soil is compacted, this is the way that the soil is compacted. There is a second kind of compaction, which is that you take some material up here in a jar and you kind of slightly tap it round about, you shake it up. And typically in most of these measurements you have a dimensionless quantity, which is acceleration that you put because of your shaker that's there. These are all sinusoidally moving objects, so a good frequency and amplitude is given up here, so that you get some acceleration term which comes from the product of the amplitude of the square of the frequency, and then you have the g and you divide it out, you get a dimensionless quantity which is gamma, and you tend to measure, how does a compaction happen. Right? So as a function of time, things get more and more compacted, and there is a little controversy about this, is how does a compaction happen. Some people find that the compaction goes like a logarithmic law, while others find that it can go like an exponential thing, and I think that it's just basically whether you are in weak confinement or a strong confinement. Let me just put in the numbers. D is basically your dimension of your container, small d is the dimension of your particles. Now you are dealing in experiments, so these are all monodispersed particles, so you have just one single d in your system. If it's of the order of 100, that people usually see exponential things. If they're of the order of 10, then people tend to look at logarithmic things, and these are kind of things that they have done for a large number of systems. If the system is polydispersed, you get a beta up here and things become a little bit more messy. You can do it in compaction. Now the compaction in 2D is interesting because typically in 2D, if you have monodispersed systems, they will form crystals. And so here you can, if you have thought about this problem, let me just go back once up here and say, suppose these were all beads of same size. If it was in 3D, then the meaning of compaction would be that, the thing I would go is a random close packing. But if I wanted to compact it any further, then I would have to have little small pockets of crystallites. Because if I can go to a crystallite somehow, and don't ask me how, but if I make a crystallite somehow because of the surface, whatever it is because of, then that will be a volume fraction which is much higher than what you have from a random packing, right? A random packing has something like 66%, that's 74%. If you now deal it with 2D, and this is what will happen in 2D, if you try to put 2D same disks together, they will automatically go into a crystalline structure, and that's almost the maximally compact structure that you can actually have, and it's very easy to go there. But nevertheless, as you put in the particles, because there is some rearrangement issues up there, there are little bit gaps in the system, and that's the gap that actually goes down while you're tapping the system up. Okay? So while in 3D people don't talk about crystallinity, in 2D there is a degree of crystallinity which also comes as you are compactifying system more and more. So let me do this experiment. These experiments were basically done by taking some discs like this. I think these were discs, and some people did with balls, doesn't matter. You take a hammer, you tap it up here, the whole thing shakes up, and slowly you get a crystal, which is usually a polycrystal. You can get grid boundaries up here and how you pack. So this is n is equal to 0. The first run, that means you have not, there is no, this is how you have prepared the system. In something like 65,000 is basically when you have done so many number of taps. And the system has gone from a height here to there, basically means that it has become more and more compact. There's some simple algorithms that people use. What they say is that, come on, let me define a particle mobility, which defines as how much each particle has moved by up. So this is a displacement, this is a particle diameter, this is the dimension of the system, this is the particle mobility, and you associate the densification factor d rho by dn to be some factor proportional to the mu, the particle mobility of the system. And if you put back all of this together, thinking that your mu is related to your density by some Arrhenius kind of a relationship, you kind of get this particular functional form up here. So, if you can put 3D piles of spheres, this is what I told you, this is semi-empirical law, 3D piles of spheres again, depending upon what you have, the dimensions you can have another semi-empirical laws, which is basically, I think this is the log law, which somehow it's not coming up here. If you have a 2D pile of disks, then it is kind of an exponential up here, exponential up here. This is the crystallization that you get, because in 3D systems you don't get crystallization. In 2D it's easy to check out crystallization. I'm sure that even here there is a little bit of crystallization up here also. So you get mobility to go like this and things and so forth. So how do you compact systems? Well, there are two ways of compacting. If you shake them mildly, then you open up little gaps, and within the gaps the particles tend to fall off. But if you are doing something like this, which is a dynamic compaction, you're going to bang against it, and then this is going to be some force chains upon which the load is being transmitted from one point to the other point. And in likelihood that when the force is large, this particular chain is going to buckle, bend, whatever, do something. There is going to be some kind of a mechanical instability associated with this particular chain, force loading chain, and that will be what will lead to compaction. So we'll first look at the compaction, which is the simplest version of the compaction that you have. This is under random loading. This is not tapping. What you have is you have something like this. Let's think of a chain of cylinders. You come up, you bang up here. You either can go out of plane in this particular way, sorry, in plane, but buckle some randomly in this direction. You can also do the classic Euler buckling, which means that I basically go out of plane. Now, so what I'll show you is I'll do these experiments with little small studs of cylinders. These cylinders are soft, they can deform. So if you have rho less than rho c, so there is some critical density, and this is within a shear cell, I'm banging it from here. Initially you have these lines that you can draw. As soon as you bang, you kind of get these non-affine deformations, and you can think that these non-affine deformations are kind of shear banding zones. These are what are the mechanical instabilities that I was talking about. The interesting part actually goes, this is again rho greater than rho c, not rho less than rho c, is what happens is when you go below or above a particular transition. So if you are above this particular critical density of packing inside the system, what you'll end up getting is the system actually packs well, but now it kind of crumples out. That little space that you have between two cylinders, and you can never have, like, even if you are doing 2D, there's always a little space above it. And within that space, actually the particles tend to pop up and pop down, and that's how you get it. So you basically get a transition from something which is like an in-plane buckling to something which is like a popping transition. The whole thing crumples out. It's a crumple zone that you get up here. And I'll illustrate how you get to this particular zone. Sure. Yeah.
You can geometrically connect through this line, so that happened because you applied this shear, or like it was the
no, it just
initial
happened because you
arrangement?
applied the shear. The moment I show you the movies, it will be clear.
Ah, okay. So you started with a random.
You starts with a random thing. This is just to motivate, what you're going to get. I'll come to the concept.
Okay.
Yeah.
Thanks.
So what you start with is some random things up here. Say this is n is equal to 1. This is what you are looking for, and then you bang it for 500 times, and you compactify here. But you essentially don't see any out of plane motions. It's kind of compact, but it shows you that kind of shear banding in the system. This is a small part, you don't see the shear banding. Then you go to a higher density 0.87 and you bang it, and after 500 times you basically see some state which is a very crumpled up state. And you will look at it that I have actually pointed something as red marks up here, so I will actually talk about rotations, and rotations play a huge role in this, so we'll get to it when we come here. Sorry.
Minimum is RCP value is limiting. I mean, you start with some random configuration. What could be the maximum?
0.87, 887.
And what is the RCP? I do not know.
92. 0.92.
0.92. Achha.
So it's okay.
And beyond, so that's the rho C.
That's a rho C.
After that,
if you get a perfect crystalline lattice, then that's what. So we'll come back to how you get to a perfect crystalline lattice, but here you don't get to a perfect crystalline lattice here. So you're very close to that number, but not really at that number. Okay, so we'll look at these questions of densification due to rapid loading, steady state configuration, what is the role of friction in the system. Obviously friction will play a big role. How do you and role of confinement. Now, let's look at the experimental setup. This is pretty simple experimental setup. What you have is, you have these the studs. These are rubber cut out from rubber cylinders. The reason we did it was because we wanted to measure the internal stress on each particle. So the deformation should be able you should be able to see them. You have a pneumatic hammer. That's some hammer which goes up and bangs against this side. It moves, and if there is internal stress developed in my system, and if those particles wants to buckle up, they can buckle up. I'm holding the whole thing up with some top plate, and I have springs on them to just hold them back. So basically I can measure the normal stress also acting on it. It gives you a little leeway, but it also allows you to, because if you don't have them, then all the particles will just fly off. Okay. Which stresses? The normal stress?
Yes.
Okay, so what you do is, you see there is a side camera up here. What you do is, you know the spring constants, you know all the spring constants up here. They're holding the thing down. Okay. You push against it, you know how much the displacement you have got. That's how you measure the normal force. Now you could just ask me whether normal force and stress, well, a naive thing is just divided by the cross sectional area. Otherwise you can go up and find out all the particles which are touching it and then take that number, but so that's how you do normal stress. Okay. So there is this experiment. What you do is, you come with a pneumatic hammer up here. This is how I prepare my system. I bang the pneumatic hammer, it brings it to some place, it just goes to some displacement, say theta max, and I choose theta max by putting a stopper up here so that it doesn't, putting a stopper up here so that the pneumatic shaft doesn't push any further. I withdraw my pneumatic shaft. Whatever be the internal stresses in my system, if there are any, then they will relax and the things will come back. So theta relaxed state. Okay. I do this experiment again, I come and I bang it again, and I look at how theta r evolves as a function of time. Remember, for every bang, theta max is always constant. I always bring it to that particular state. I push it into that particular state. So what you can do is, you can start measuring. First term that you can see is how this gamma n, and I'll tell you what gamma n is. Gamma n is theta r, that you remember, that how much angle it has come back to, by theta r0, which is that n is equal to 0. First time how much it came back to, you divide these two up and you start looking at them. It kind of gives you a stressed exponential decay in the system with a beta of 0.3. You can do it as a function of density, and you basically get some kind of a dynamical transition in the system, that at some point you get many more cycles before you actually go to a steady state. So at the steady state, and somewhere up here, you need many more cycles before the system can reach the steady state. What you can do now is, you can actually tune this relaxation time scale, which here is just the bang number that you have, and that you do by changing the friction in the system. And this we found was interesting. If you have a low friction system, this is mu is equal to 0.52, and I'll tell you how we get this is that these are particles, and we coat them with a paint, very thin paint, which is a Teflon kind of a paint, which gives them so that the particle frictions are very low. So that's 0.57. You get something like this, which is the sharpest transition, and it's the lowest density that you have. You go up to 0.82. This is where we have the uncoated particles. You don't have any coating on them. So this is rubber friction. This is mu is equal to 0.82. The transition point goes up here, and the other thing that you can do is, you can make it to a high friction state. That is, you put a grit paper across it, so that it's a very high friction system, and you see that what friction does is, as I go up in friction, my transition is almost killed. Right? You can, so the exponents don't change much. Well, you can, this one I don't even know whether there is an exponent or not, but it kind of gets killed, and the transition point actually also shifts from left to right. And that's not very surprising, because you see what the friction does is, the friction actually doesn't allow particles to move up. And this particular transition has to do with something where the particles are slightly going out of plane. If you prevent particles from going out of plane, you don't tend to see this particular transition. You could do the same thing as a function of theta r. That means how much it is relaxed back. And this is so this is the theta rs. So you go back, and this is the theta rs. This is the base value to which it comes back to. And you can measure that. Mu is equal to 0.57. Again, shows you a nice transition as a function of density. 0.82, it's already getting iffy, the transition. and I think 1.79, I won't even call there is a transition up here. So friction kind of kills the transition, it's a stabilizing factor. Yeah, sorry.
So if it is steady state, do I expect that theta r will not change anymore?
Yeah, it's okay, in give and take. I'll just let me just show you the data. Give and take. This is the fitting parameter. So you will not see it change much. It might change a bit, but it won't change much.
That also demarcates steady.
Yeah, you just fit to these are extrapolated numbers, right? So that's what it is. I didn't actually tell you what the transition was actually. I just said there is a transition.
Okay.
Well, I'll just tell you what the transition was, and I kind of told earlier than this. The transition was this. So at some point, what you have is as you bang, you see what will happen when you have a transition. When you have densification, you must be getting rid of these little void spaces, right? That's one way of getting rid of void space. The other way of going is by going out of it. Look at things. If I want to crumple it, if I allow some space up here, it will crumple and go there. So if the first phase, that means left of the transition, is where only in-plane arrangements happen. The right of the transition is when particles tend to go slightly up and down. They kind of go up and down, and that's in a very highly internally stressed out state. So you have a lot of stress being generated into the system. They don't relax the state. This is because the particles, when they go up, they kind of get slightly tilted out, and that's what they dig into the surface much more. So that's the transition. The transition is between whether particles pop out of plane or particles don't pop out of plane.
Right. So just I'll interrupt for 1 second. So when you say bang, intuitively there feels like some elastodynamic should be involved as well. So is there any wave effect or elastodynamic mediation of those transitions? So is there a dimensionless number or any quantification that we can think what role the friction plays and what role the elastodynamic plays? Any competition?
No, we haven't actually looked at it because I'll tell you why it is difficult, and at some point I'll show that it's mainly mediated by rotations in the system, and I don't know how to handle rotations in this kind of a mechanism. The individual particles can rotate, and that plays a huge role in this transition. So I don't know the answer to that question. Okay. So we said that that friction kind of stabilizes the whole thing. We could look at the densification, and well, what you can do is you can plot the density of the system, and as a function of n, and these are your saturated densities. That is the maximum densities that you can actually push the system to. But what I did not tell you is what was this densities that I was talking about when I plotted. What was this density that I was talking about, rho, and that density was, I should have said this, that if you go to this particular state, when I bang the system up, then in this particular state, what is the maximum, what is the density of the particles? That is the density that I am quoting. When I add particles, that's the density that I am plotting on the x-axis. Remember, otherwise in the relaxed state, the density is an evolving parameter, so there is no unique density for that. So when I plot something as a function of r, rho, this is the density that this is the maximum density the system can go to. So what you can do is you can actually go up and see this rho r as a function of n, and this kind of saturates to some different densities, and these densities are basically the density in the relaxed out state. If you now use these densities on the x-axis instead of putting in the values of rho r's rho's which I had earlier, so remember these plots, instead of plotting it this particular way or this particular way where rho was defined as the density in the maximally compressed state, if I took my saturation density, then it kind of all of them kind of collapses and gives you a particular number, and this is about 0.85. So it means that the effect of friction is to prevent the system from going to that particular density, accessing that particular density, and that's how it happens. This is two-dimensional system. You could look at defects in your system and quantify the defects. Well, at time, the defects actually also come down, the number of defects. This is a fraction of defects that you have, and the time scale required to get these defects also has a divergence. So let me just tell you, these defects are basically how many are there 6 and how many are there 5 and 7 and things like that. So there is also this other question about what about the local stresses in the system. You can quantify them in terms of the eccentricity in your system. So you can see that if I have a highly compressed state, so this is 0.86, initial eccentricity is high, but it takes a long time to actually go down to some value, where in its large n limit, it actually, the eccentricity kind of has a finite value, but lower than what you started off with. And then you can do it, the same thing you can do it with a lower density system. Similarly, the compression will also tell you that you come up here and you basically start to increase in your eccentricity, which tells you that the internal stresses are built up in a state once you cross into the compressed state. Oh, what you do is you kind of take inner circles of every cylinder, you fit a cylinder to it, ellipse to it, and you measure the major and minor axes to it. So that's what you do. And this is one reason why you see that these are all black. This is important that you get the black substrate at the down, so that you can actually find out all these ellipses out of it. Okay. So let me show you the failure modes first. I have not talked about the failure modes at all.
Can I ask one more?
Yeah.
Yeah, so is there a particular reason like why you don't feed the outer circle, only the
inner circle? Oh, okay, there is no. We found it easier to fit the inner circles.
Okay.
Because outer circles you have 2 points touching, right? So your Hoff transforms run into a problem. It's much easier to do it with the inner circles. If the outer circles do something else, and across that boundary if there is something else, we don't know.
Thanks.
Yeah, so this is the experiment that you have, that you come, you bang. This is the very first time that you can bang the system. If it's lower than a critical density, if it is higher than a critical density, and I don't know whether you noticed or not, but there is an overall buckling in the system. So it stops and it buckles, the system buckles. Okay? And you can kind of quantify the system in a way that, well, this is my velocity of my plunger. Initially the velocity just increases because it doesn't hit anything, and then the velocity decreases because I now start to get the resistance from my system. Up here there is a rejuvenation. At some point the system starts to provide me resistance, and this is where the force network chains start to form, this part of it. And once this part is formed, you can stop, it will slightly slow down, and then again the velocity will fall off, because then finally those chains will break. So here is the chains are breaking up here, and then again the chains are forming. So this is the whole thing which you have the in-plane thing happening. You can see it for the other thing, that you see it almost comes to a halt, it breaks and then goes up. So you basically have, when you have critical density, whenever the density is greater than a critical density, the speed, it kind of slowly goes up for a longer distance. So if you just even look at the plunger speed, it's very different when you have things below the critical density or above the critical density. It's much drawn out up here. Sure. How am I controlling? This is a compressor, and I'm monitoring the compressor. This is a pneumatic shaft coming in, banging. So you have it's a pressure control. It's a pressure control, and pressure is monitored. You can do a bit of laser scanning profilometry to figure out how many particles have popped up in the system. So if you are below a critical density, then for the first run almost these are flat, but the moment you go below a critical density, you start getting that these things buckle out. This is normal classical Euler buckling. You can measure this height. This is an average height of measured along this particular direction. You can see this as a function of this average height as a function of density. If you are below a particular critical density, then it's flat, there is no out of plane buckling, then it starts to buckle. You change your friction factor, things don't buckle. You can go to very high densities, at least initial high densities, but with high friction, there's hardly any out of plane buckling. So out of plane buckling is being suppressed by adding friction in my system. So this is how I measure my top plate. This is how I measure the normal stress. As things pop out, this springs get compressed. I know how much displacement I have here. I know what my normal forces are, and this is what you do. You measure the normal force. Again, the same thing. Below a critical density, the normal forces don't exist. After a critical density, the normal forces start to come up as particles come up more and more. Now, what really happens is, as you cycle out the whole system, you saw that the system actually buckled out, and then as I relaxed back, this buckling would come down, and then again some particles would buckle up, and then some particles would come down. But if you're around the critical density, what would happen is some particles would tend on to come up, and they would get reinforced. So whatever buckled up, not all of them will come down. Some of them will come down, but not fully, and those particles are like the weak spots, and they tend to get reinforced over and over again. So next time when I bang it, they will go up. So over time, and so this is what will happen is, you can go up and look at your which are the buckled particles, and you will see that over time the number of buckled particles will start to increase. So this is a fraction of particles which are buckled, and you see that below a critical density none of the particles are buckled. These are buckled means these are popped out particles, sorry. This is the structure, not the global buckling. This is incoherent popping off of the particles. And as you cross the critical density, when you have reached a steady state, then the number of popped up particles increases in this particular way. And again, here you see what the role of friction is to not allow particles to pop up. Only few particles pop up. Oh, this is like 1.2 cylinders. It's just a little gap. It's almost positive dimension in that sense that, and this particular experiment, by the way, is known by any experimentalist who has worked on this system. Nobody's followed it up, but because we don't want to have large friction, we always keep a little gap on the top. So whenever we do experiments, nothing is exactly two-dimensional. You really have that little gap on the top always. So this is what we wanted to show you, is this, as you start pushing the particles, you see the particles which pop are also the particles which tend to rotate. So you pop up, you go up, it's a helical motion. So let me just show you. This is how you get to do this. You come up, the next time you go up a little bit, next time you go up a little bit, next time you go up a little bit. So there's a lot of rotation in the system. So you suddenly start to the particles rotate, and that's how they start to pop up. You can actually quantify the fraction of the active particles. Active particles means how many particles have rotated and how many particles have not rotated, and you can quantify that. And it also looks like a weakly, but it looks like something is happening at about the critical density up here. So now that I have told you about how many minutes? 20 minutes. Okay, fine. That's exactly. So now that I've told you about what happens under rapid compaction, let me tell you something which happens under really, if I shake them slightly. This is where physicists, this Chicago group and others have done experiments. Take some grains and slightly shake them. I'll tell you what is the protocol of our shaking, and we'll do it in 2D. There's this problem with 2D is that though we know that every 2D system is, it will back at about 0.92 actually up here. It's a kissing problem that every disk will actually touch 6 other disks in 2 dimension. But if you try to lay them down on a table, for example, you try doing this, and somewhere down you make a mistake because there's friction, whatnot, and the problem is you will never be able to undo that mistake. There is no grain, so it starts spreading all over the system, and you will see that lots of errors that comes up here. This is what kills this is why you get polycrystal in your system. So there's a lot of polycrystalline domains in your system. And the question would be that I start with a system like that, and if I want to densify the system, I want to go to a system like that. And how do I go to this system, right? So here is the whole idea that I come with something, I start with like that, lots of grain boundaries. I basically want to a system which I define to say either has point defects or has no defects at all, 0 defects. Point defects are very difficult to get out of the system. What do you do? Now it turns out that people have looked at this problem, at least in simulations, and these are some random organization models where you put in some games where you say that, I will move the particles, I'll randomly move particles, and if there is an overlap, then I'll move these particles by some random directions. And these are people who actually looked at it in 2020. This is slightly later than our paper was published anyway. And they found that this is the fraction of particles that are active, and they find that this is also a dynamical phase transition with an exponent which says that fraction of as a function of particles that are active goes with a factor of 0.42. Then there is a time divergence in the system which has an exponent of 1.33, and this is the steady state value. This is this value that how many particles are active. Active particles means how many particles are actually moving at the end of it. And if nothing is moving, it's like this. It's an absorbing state. So that exponent is 0.64, and F infinity means how many particles in the n is equal to infinite limit. Anyway, so typically for normal systems, this is a shear. Shear is area conserving. If you do simulations, practically in experiments, it's not area conserving. So this is why we have little gap on the top. This is our experiment that you use gravity up in your system. You kind of shake these things from the bottom by moving the linear stage. So think of these two arms as two pendulums, and they're just doing this in the system. So you start with the system up here, you go to that state, so that means you have pushed the particles to one side, you come back to again the initial state, you push it to the other side and come back and complete the cycle. That's what you do. And I'm going to show you some strobed images. This is only strobed images. I start here, I go back here. I could have taken strobe anywhere, but anyway, I will just show you the strobed images for this. And this is for a particular critical density. This is what happens, and I'll show you. Then I'll tell you what happens at other densities. That if if you have chosen the right density, then you start with a random configuration, and slowly you anneal out all the defects in your system, and you are left with one nice state in the system. If you're worrying about why these particles are hanging, if there is an angle, this is critically chosen that the friction is just balances off there, but there are always some particles which tends to get stuck up there. Sorry, I didn't hear. Oh, I could play this again. Oh, sure. So you could look at individual trajectories in the system, and these trajectories, they are not time reversal, so there is no reason for the particles to go back in the same path. They come at some complicated paths, and these are typical paths. This is on the left hand side of the image, this is on the right hand side. They have some weird paths. Typically this and that, left and the right side of the images, they are kind of symmetric. In the inside there is some H-shaped object. So these are complicated trajectories that each particle does. But interesting part of it is they kind of come back to the same place. See, if you are in the steady state, if they did not come back to the same state, then there wouldn't be a crystal. It would just have got defects all over the place, right? So this is a typical trajectory that I'll look at. It's gamma. Now it's not density. It's how much amplitude I'm giving to it. So if gamma is less than gamma c, you kind of have closed loop. Give and take. This is, you can doubt whether this is a limit cycle or not, but it's a closed loop kind of a thing. But if it's gamma greater than gamma c, then you basically have something which is diffusing all over the place. This is certainly not the right parameter. I'll tell you, even this is not the right parameter. The gamma is equal to gamma c is the right parameter. Oh, just now now what I have in this system is I had this particular and this is my system. I'm not changing the density because it doesn't make sense of changing the density. I can only change one parameter in my system, is basically how much I am disturbing the system. So that's why I'm doing this. In that other period, the disturbance was kept constant and the density was changed. Here the density is kept constant, the disturbance and the protocol is changed. Sorry. Oh, you couldn't do now, because if you didn't have the free surface, then it's not an area conserving thing. So
that's fine, but
sorry.
I mean, if you take free surface, then allow for the location of the
So would you say that is the pressure on the system important? Is this the top pressure? I'll answer that question. Actually, it's very important. It is crucial to the whole thing, and I'll tell you this. So you could measure, this is alpha s is the active particles, the end of the story. So active particles again is the particles which are moving, and you can see, there is some time scale, how long it takes to actually get to a steady state. There is a divergence, and this is again 0.75. This 0.75 was exactly what I had seen in the dynamical system also. This criteria was about 0.75, the exponent. You could measure this, which is basically the absorbing state Fs, which is Ft for the theory calculations, and this is the fraction of active particles in your system as a function of gamma. If you are below a critical point, then everything up here is absorbing. So essentially, this value is 0. Once you cross it, it becomes like that. So here you get kind of these kinds of loops. The loop becomes very tight. Sorry, this thing should have been marked here. Once you cross over here, then it's very, very absorbing. It's very, very chaotic. You could do the defect density up here. There's a Voronoi tessellation problem, but you could also do psi 6 and whatnot, everything. And essentially you could measure the defect density as a function of n again, and you'll find that the defect density also comes down, and that also has an exponent that also has a power law character at about gamma c. This is just to convince that you can do the psi 6 parameter, and that also has a peak up there. So at this particular point, so you can just look at, maybe I should do this. At this gamma is equal to 0.65, you actually have a monocrystal, one single crystal. If you are lower than that, these fault planes are not annealed. And you can think about it, and look at this gamma, this is really tiny gamma. I'm really moving little small parts actually. No, it's not really exploring much. If you are at very large gammas, then obviously you get lots of defects in your system. If you change the size of the system, so you can go from say I did 7, this is 8 and this is 9 probably, and you see that this will actually start to shift. This is the defects that you have. It goes to 0 here. This also goes to 0, but the point of this is shifted. This is shifted from here to there. You can measure the gamma c as a function of d, and it looks like that the critical strain actually has a linear relationship with the dm. You could push this thing much further, because then you started getting other kinds of effects in your system, because if you get very tiny particles, they don't remain two-dimensional, they tend to buckle out of plane. So this is the question that Pinaki you were asking, effect of gravity and pressure. So if you did this whole thing, and if you said that, when I said that, I've got to a state which is non-absorbing, what part of it is non-absorbing? So if you do the system, you'll find that this is the trajectories of some of the trajectories. You'll find that there is this lower part. So this is, remember the gravity, this is the gravity is in this direction. This is lower part of the system where the things are always absorbing. Is the top part, the melting is always happening from the top part. So if I had applied a pressure on the top part, I can actually suppress this entire melting phenomena up here. Right? So if you're in an absorbing state, then this particular parameter L is 0, which would mean that if I look at these trajectories there, you can see all of them are beautiful trajectories. They're all closing up to each other, and that's what you have in your system. If I'm diffusing, then L is greater than 0. That's the L that I'm talking about. And you see the top part has kind of diffused. The bottom part is not diffused at all. And you can measure that L as a function of gamma. In the absorbing state, L is equal to 0. This is what I said. All particles come back to its own position. If you're an active particle, then it kind of goes up in this particular direction. It's a linear, whatever, I don't know what it is, it's some function up there. You could just estimate an order of magnitude calculation saying there is a normal stress in the system, and the first layer has to melt before the gamma c can happen, and you can balance this too. So this is the sigma z, which is the strain value, and g, which is the elastic constant, which balances the rho gl term in your system, and that gives you a gamma c in your system. So that you say the gamma c goes like linear, but that's a hand waving argument of doing so. What about rotation? In this system, we didn't get some great physics about rotation, except that we realized that not all the particles tend to come back to its own position. I mean, almost nothing comes back to its position. So if you were, so even in the absorbing state, if I were to track the angular position of the particle, they don't come back to its position. It's only the center of masses which come back to its position. And I think it's trivial to understand why. Because if I'm pushing these particles up here, then these two walls are not the same, because this is not a continuous fluid, right? So this wall is a pusher, this wall is a puller. You can't really pull on granular systems. So they are just a confining wall. Rotations happen here, and translations happen to particles which are on this side of the wall. So I rotate, I go this side. When I do this side, these particles rotate, but these particles translate. So you tend to build up rotations overall in the system. You can do the bidisperse system in your system, and well, it just shows you similar kind of behavior, except that the exponent, so let's look at the exponent. So random organization exponents were about 1.33 for relaxation time. F infinity was like alpha, so that scores like beta was 0.64. This term is kind of 0.8, 0.64, you know, this is a plus minus about 0.2 about. So this could match up the F infinity parameter. This somehow for a monodisperse system is 0.75. Bidisperse system and random organization have the similar kind of numbers. This is 1.33, that's 1.3. But the monodisperse system seems to be very, very different. It's a number of 0.75. This is also the number that we get from the random dynamical compaction. There also we get at 0.75. I have a feeling that with monodisperse systems there is a lot of buckling and things like that going out in the system, and that could be one reason why these numbers are different. So they look like monodisperse and the dynamical compaction are similar kind of problems, whereas random organization bidisperse are similar kind of things. Yeah. So we have two dynamical transitions in the system. One that came from cusp where you have a highly ordered state happening in your system. The other was an active to an absorbing transition. Are these two transitions coupled? Are they connected to each other? I don't know. Is it serendipitous that they happen at the same point? I'm not sure about it, but that's where our results are. Thank you.
Yeah, fascinating talk, and it was, I mean, the illustrations were really, I mean, provokes questions and interesting comments as well. So again, when you say mu's, those are friction coefficients, right?
Yeah.
And you have 3 different values and 1.67 as well.
Yeah.
So it's friction between who? Two cylinders?
Sorry, okay. This is the experiment. I'll tell you how do we measure the friction. Actually, friction here is also not an easy way of measuring it out. So this is friction between the two cylinders. That's what we have changed. But you could ask what friction is this, because it could happen that, you know, it's rolling or. So this is the experiment this is how I measure the mu. So what you have is similarly 3 cylinders up here. Okay, the inner cylinder is the one which I want to measure the friction of. These 3 cylinders all have the same kind of coatings on them. I put a load up here and see when it starts to rotate. So in some sense, I'm seeing a rotational friction in my system. You know, it's a rotational sliding. It's a I don't know what friction am I seeing, but it's a friction between the particles.
Okay, so there is no rate effect or anything other effects within that while you do the averaging or something.
So these are extremely slow experiments. I'll tell you, for these experiments, well, these experiments are not slow because, you know, you bang.
Yes.
And so there would be a lot of time dependent phenomena in it, and I would be very surprised if there aren't any. Unfortunately, we have not got to another material. We would have loved to get to another material which we could do it, but you see, the thing is that we don't want things to topple around, and all those are practical problems. But we haven't got another material, so there could be time dependent effects in it. I will be very surprised if there is no time dependent effect in it.
And again, this is for my own takeaway home messages. So why, when you say buckling, so I mean, that is generally when we do very slow loading, and then at one point there is a bifurcation. My So intuitively, why it seems counterintuitive in a sense, it may be just one, again back to the same point, there is a wave which doesn't get enough time to fall back because of the friction.
Yeah.
So are they two
So
same?
you're saying rightly, right? You're saying that because you have a time dependent forcing term in my system, my Euler buckling equation, the Euler buckling, it doesn't give me that solution which is just one particular. It has a combination of all kinds of modes in my system. So why do I get one? So it could be what I call as an Euler is that you see what happens is it stops.
Yeah. So
Loading stops and then it starts to push.
yeah. So what I fail to take away is that instead of it's a buckling, it may be there is inertia effect involved of the individual masses, and hence it is elastodynamic or wave mediated things rather than just. So in what way I am incorrect here? That's what I want.
No, I
to
don't know whether
understand.
you're incorrect or not. I said buckling in a sense that it looked like a buckled structure. So it was more like to explain the whole thing. It was
story part.
It wasn't really. I was not saying that this is the Euler buckling limit. I was not saying this is the static Euler buckling statement. I was not making that sense. It just looked buckled. I said buckled.
Okay. Yeah. Thanks. Yeah.
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 How does that influence the packing?
No,
and the
so what-
rolling basically.
So what really happens is, what you get is you start to get, so these, it's okay. So typically what happens is if I'm doing this, I'm putting a force and I'm putting an acceleration, then you have a mass matrix in the system that connects the two. Now, every time about this axis when I'm loading it up, these particles tend to splay around a bit. And as they splay, then the force now has a component which digs them into the substrate. Now the frictional component, so what is preventing them from going back? Why is it like, I'm being held at a much more compressed? It is because friction is now much higher, it plays much more higher, because the orientation of the particle, the way it's touching the plate has altered. So typically in the first low density system, I was coming in, all these particles were flat on my system and I was just doing this. So, friction didn't change. But now these particles have got a little bit of splay in the whole system, and that allows the system to actually support. Finally, it has to be a force balance. The force is coming both the top plate and from the bottom plate.
My question was more related to how the properties of the frictional interface evolve as you hit them multiple times, because each time there's a loading
So
and
what we
unloading
do
history
is-
on
so-
each particle.
So what we do is, typically we repeat these experiments over and over again without changing the particles themselves, and the results don't change much. So I would say that overall, if you say fatigue of the particles, if that's what I'm pushing in, maybe I'm scratching the surface, maybe the particles are getting, because after all these are rubber, right, neoprene rubber, I think diluted in rubber. So I think whether those matter or not, over the scale of which we have done the experiments, that 50 cycles for each experiment, they haven't changed.
Yeah, Purushottam.
The slide showed that very strange. There's a development of fracture or void. So
Yeah.
what's the notion of that fracture? I mean, how would you know that this is the void?
Which one?
In one of in one of your slides, you showed that it is strained. There's a development of voids or fracture. You mentioned that.
Okay, so was it this?
Well, no, not really. Before that, maybe. No, this is the before that.
Before this?
Yeah. Well, no. Yes.
Oh, this
yes,
one.
yes,
I
yes,
know
there,
this
right.
one. The tear that you
How
have.
do you,
That little tear up here, right?
Exactly.
I don't
How
know.
do you know that? I mean,
I don't
what
know.
is
I don't
the-
understand it. Yeah. So there is some load-bearing structures, and those load-bearing structures playing out.
Yeah, visually I can get that, I get the feeling, but
Yeah, I don't.
if I have to
No, I don't know.
quantitatively,
I don't know.
Yeah.
It looks as if there's two arms. So the way I would have thought about it is the two load-bearing arms. You're pushing on the two load-bearing arms, and they're kind of bending around. That's how I would think about it. Because this is under a at this point when it's playing, it's actually highly compressed. These lines are very compressed. It's load-bearing structures. We tried doing it with friction. I thought that friction would do that. Well, friction just killed everything. Yeah, and that is true. That is true. We didn't do it. We didn't put in a thing. Yeah, we didn't put. When we started the experiment, we thought that what we were doing is somehow. In my mind, I had addition and friction in a similar way. This is why I did it. Yeah, could have. Yeah, I could have done that. Yeah, some sticky polymer probably. Yeah, I have not done that. Yes, this experiment is done.
Thank you. In the second case, how does friction plays a role? How does it delays the annealing or something?
Okay, so in the second case, we haven't found the role of friction at all in my systems. We have tried playing around it. Okay, what really happens is, okay, I'll give you the. So if you look at these loops, the only role that friction plays here is, if you look at these loops are not really great, these ones, because they don't come back exactly to the same point. What we did then was, we couldn't change the friction, it's not easy to change the friction. We put in a lot of ultrasonic speakers on your glass bead so that they kind of shake the whole thing up. This is called as vibration induced lubrication, because you're doing that, your substrate interactions have gone down, these loops become very tight, so the transition becomes much more cleaner. Beyond that, we haven't seen any other effect.
And what material these beads were?
This is laser cut with these are acrylic. These are acrylic discs.
So for the active absorbing transition, is this university class known, or is it sufficiently distinct from everything that
it is distinct, because if I've got something which is very different, 1.3 minus 1.3 is what people have seen in random organization, but we get some very different number, 0.75. That I don't know why. I don't think that there is anybody who has reported that number.
Also, it changes within the same dimension, doesn't it?
When you're showing these loops, this is the actual position, or
the actual positions?
Okay, so it's not the non-affine deformation. It's just
no, this is actual positions.
Okay. So, what do you think how this will translate to non-affine deformation more or less?
You can actually look at these. I'll show you. Oh, non-affine deformations. Well, okay. Yeah, I don't have it here. They're very complicated structures that happens. But I don't have it there. You're wanting the one for which there's a very rapid loading of the system.
Because I guess the shape has to do probably in the position of the particle.
Yeah, so if you look at it, maybe I can give you a quick answer to this. Sorry, here it is. You look at this particle, this is over the entire thing, and I'm not plotted all of them, I've plotted some other, it's been very crowded. So these ones are like, less loopy, I mean the holes are less. This is moving the maximum, because that's the bottom plate which is moving, so that's why the loop is extended up here. These ones are like more loopy up here, the ones at the boundaries are loopy. And this is also because these are rotating particles. All these particles are mainly rotating. Anything which rotates actually gives you more loopy kind of structures.
So there must be many more questions which you can continue during the lunch time. And let us thank Shankar for a fantastic presentation of the work. And we had very interesting non-thermal thermodynamic systems discussed in this session. Alex and Shankar, they presented us some of the very exciting